Hello, everyone. This is Dr. White here with a little help in the form of a screencast on the topic of data wrangling, Chapter 4 in our textbook. So why don't we go ahead and get logged into our studio and get started. So this is the first part, the first unit on data wrangling out of 2 or 3 such units. And this set of slides, the Chapter 4 of Part 1, I'll cover maybe all in this screencast, or maybe I'll divide it up. I'll sort of see as I go along. It's a nice sunny day, summer evening. You can hear an ice cream truck in the background. I don't know if I'm in the mood to go through the entire set of slides, but we'll see what happens. So within the big picture of data science that we're always looking at, data wrangling is part of the transform phase. That's an element in this kind of circular process. Transform your data into a form that makes it suitable for visualizing with something like ggplot2. Possibly make some models off of that transformed data as well. That's a subject that comes in later chapters. And then having acquired some understanding, you might get some ideas for transforming the data in yet another form, which you then will visualize and model and so on until you feel like you've gained some understanding of the situation. So data wrangling is wrestling with data. It's maybe a little bit like wrestling an alligator, where you try to get the alligator into a position that you want it in. And so you got to be tough, you got to be prepared. So let me give you a little motivating example that we will use to kick off these slides, and then we'll, once we acquire sufficient tools, we'll come back and actually solve the example. So I'd like you to learn about a new data set, the NCHS data table that's in the package data computing, which is installed on the RStudio server. Now, if you would like to get access to just one data set out of a package without having to attach the entire package to your R session, you can do so with the data command. And then you can ask for help on the data set, but since the package is not attached, you'll have to include the argument package equals quotes the name of the package that you're interested in. So I'd like to go ahead and learn about this data set. So let me go ahead and copy, and we'll paste this code into maybe some notes over in RStudio. So I've got RStudio set up here, and I've got some notes, and since I'll be doing data analysis, I should probably attach MDSR to my session right now. And then just copy in. And we'll first run the data command. And so over in your global environment, you notice that the data table NCHS comes in on a promise. It's sort of like not quite read into your R session's memory yet, but it will be when you ask to do some computations on it. Let's get some help. And up comes help file, which I'll pop up big for a moment. So NCHS is health statistics data over a 5-year period from 1999 to 2004. It's survey data on a large number of individuals, about 5,000 each year. And this particular data table covering 5 years actually has information on 31,126 people. Every row in this data table is a person, and the columns are variables that are measured on these people, such as their sex, their age in years, whether or not they are pregnant, their ethnicity, and so on and so on and so on, getting on into all kinds of body measurements and health information. Okay, so what would we like to do with this data? We would like to make the following graph. So this is the graph you see on slide number 6. So what you've got on the x-axis is the age of a person, but grouped by whether the person's in their 20s, their 30s, their 40s, 50s, 60s, or maybe 70 years and older. So apparently people under 20 are not involved in this graph. And you see two line graphs in the same plot. So apparently we've done some aesthetic mapping where color has gotten mapped to sex. And on the y-axis is height, well, mean height in meters. So each of these points actually represents a group of people. This point up here where I'm waving my mouse, this little square point, is the set, or represents the set of all males in their 20s. And you can tell because it's over the 20s on the x-axis, and apparently the mean height of these males is a little over 1.75 meters. And of course, as you see, the heights go down as the age group goes up. That's not really because people are shrinking as they age. Remember, these are different people. They're not same people measured like over a long period of time. So what you're really seeing is that younger people, younger adults now are just taller than adults in previous generations were. Same story for the females, except that their average heights are smaller. So we're thinking about, like, how did we get this graph? And the key is to get that data into what we call glyph-ready form for the graph. A data table is in glyph-ready form for a graph when the plotting system, in this case ggplot2, can correctly associate cases of the data table, that's the rows, with the desired glyphs. And that's where data wrangling often comes in. You've got to wrangle, manipulate your data to get it into glyph-ready form. Because let's think about this. What's the glyph-ready form for that plot that we looked at? For our target plot, the cases would be sets of people. So a glyph-ready data table would have like a row for all females who are in their 20s, and it would also need to say what the mean height is for that group. It would need a row for males in their 20s and say what their mean height is, and then so on for the 30s, 40s, 50s, 60s, 70 pluses. Two rows for each of those age groups. And so those would be the cases in a glyph-ready data table. They are not the cases in NCHS. In CHS, every case, every row is a single person. So we obviously have some transformation that we need to do. So at this stage, you should, now that you sort of know where you're starting in terms of NCHS and where you want to go, the data table, part of which is shown on this previous page, then you want to draw up a plan. And that plan can be done just by writing by hand. What kind of plot you would like to see. Now here, I just showed you the target, but, before you actually make your own graph, you probably would just need to kind of free sketch roughly what you think such a graph might look like. And then you would write down by hand a few lines in that target table. And then you would write up your plan in ordinary English. And that plan would be a sequence of steps that you need in order to transform the data. Now, you're not going to know right now what those steps are. You got to learn them. But once you've learned them, you'll know the names of the steps and how to write up such a plan. Don't neglect this step of planning your wrangling. It's something that you do away from the computer. You don't just jump in and code. If you don't plan your wrangling, maybe you'll end up like this guy. So, what's the wrangling plan here? Well, the target graph didn't include any age groups for below 20, so you're going to have to drop the people under the age of 20 from the initial data table in CHS. And secondly, you're going to have to do something about the age of the person. You know, in the original data table, age is given in years. We've got, instead of the age of the person, we need to know what age group they're in. So we're going to have to create that new age group variable. Thirdly, we're going to have to divide the table up into separate groups, one for each age group and sex. You know, males in their 20s, females in their 20s, males in their 30s, and so on. And then once we've got that data table divided up into these groups, we've got to compute the mean height for each of these groups. If we do these steps, then we can arrive at this target glyph-ready data table. So, what does this look like in R code? Well, there's kind of a conceptual framework that guides how you think about this when you're doing it in R. So let's take a look into it. You're going to learn various functions, R functions, for wrangling data. And they come in three families. First, there's reduction functions. Now, reduction function is going to take a variable, like a column in a data frame. So that's a lot of individual values stuck together. It takes a variable as input, and it returns one single number called a scalar. Secondly, there's transformation functions. Now, they'll take one or more of the existing variables in a data table as input, and they will return a new variable in that data table. So instead of just one number, they return a whole bunch of numbers that becomes another column in your data table. Transformation functions. Thirdly, there's data verbs. Now, as input, they take an existing data table, and they do something to it and return a new data table. So data verb, data table in, data table out. And you'll find that every step in the wrangling process is going to involve a data verb and one or more reduction or transformation functions. Now, these functions, reduction functions, transformation functions, and data verbs, they come from various places, but a lot of them reside in the R package called dplyr. D for data, maybe, plier, as in I ply my trade, and R. So it's you're applying your data wrangling skills in R. Now, this package, dplyr, is automatically loaded when you attach the MDSR package. So you've already got it attached to your R session. Okay, let's dig in and look at these families of functions one by one. Let's go first for the reduction functions. So remember, they're functions that take a variable and give you a scalar back. So they tend to reduce or summarize a variable down into scalar form. If you've done any programming before, you've probably met them. If you've done statistics before, you've probably met them. You just don't know them as R functions necessarily. So the mean. You know, if you take a bunch of numbers and you add them up and divide by how many numbers there were, you get one number back called the mean. So that's typically that's a good way of finding a single typical value that like says what the other values in the list, might be kind of close to. Median. So this is another way of describing, a typical value for a data set. So here you take a set of numbers and you order them from low to high, and you look for the one that's closest to the middle, and that's the median. Standard deviation is a measure of how spread out the set of numbers are from their mean. So you can take the standard deviation of all of the values in some variable in a data table. There's a very simple looking function called in, and it just says how many rows there are in a data table or in specific groups in a data table. We'll see. The minimum and the maximum of a set of numbers can be found with min and max. There's a nice little function called indistinct. You give it a set of numbers, and it will find out all of the unique values. So if you give it like 2, 2, 3, 3, 3, it'll just come back at you with 2 and 3. It doesn't count repetitions. Many other reduction functions. Transformation functions. So remember, these are functions that take one or more variables in a data table and give you a new variable for that data table. So a lot of simple functions that you've worked with before are actually transformation functions. You can add two variables together, element by element. You can subtract them, you can divide them, you can multiply them, you can take their logarithm, you can round them off to the nearest whole number. And as we'll see with examples, when you give one of these functions a lot of numbers in a variable, you'll get a lot of answers out. In addition, there are transformation functions that are called logical ones because they create a new variable that's just made up of trues and falses. We'll see things like less than, bigger than, less than or equal to, bigger than or equal to, or checking to see if two numbers are equal is done with equals equals. The %in% function that we're going to meet is also a great logical transformation function. Another function that we'll meet because it's specific to this example, but it's certainly useful in lots of places, is the cut function. Here's an example of the cut function. Let's go ahead and give it let's just copy, paste, and run this code, and then we'll talk about how it's working. So head to RStudio, and let's first run the sum speeds line. And so we create a little vector of 8 numbers, 10, 35, 23, 67, 44, 85, 79, and 19. And maybe we can think of these as, I don't know, the speeds at which some people drive a car. And we want to label these speeds. We want to group them together as the slow speeds, the medium speeds, and the fast speeds. And let's just say that a person drives slow if they drive less than 30 miles an hour. If they drive from 30 to 60 miles an hour, then we'll call them medium speed. If they drive faster than 60 miles per hour, then we'll call them fast. How can you start with that vector of speeds and get a vector of slow, mediums, and fasts? The cut function is your way to do it. So let's run the cut function on some speeds. And we get the results down here in the console. We get 8 words: slow, medium, slow, fast, medium, fast, fast, slow. We also get a report of what the levels were. Those were the 3 possible values: slow, medium, and fast. And it works. 10 miles per hour is slow. 35 miles per hour is medium. How is it working? Well, the first argument to cut is the vector of values that you would like to cut up into groups. That's the sum speeds. The second argument is determined with a breaks parameter, and that tells you how to make the groups. What you do is stick together some numerical values with the C function, and anybody who drives less than 30 miles per hour I want to count as slow. So that person could be anywhere between minus infinity and 30. So like inf is actually a number in R. And minus inf would be like less than any real number. And then we write in 60. And so the 30 to 60 is going to make the next group. And then we write in another inf. And so R understands that 60 on up is going to be a third group. Next, there's a labels argument to the cut function. And you need to have one less label than you had number of breaks to make it work out right. And the labels are slow, medium, fast. Makes sense to me to use that choice. Now, what's this right equals false all about? That tells you which side the open endpoint should be when you break things up into groups. Let me just show you what's up by taking away the labels argument, which is not really needed. And let's run the cut again. And when you're not provided with labels, then R makes up labels on its own. And so the slow speed was given as minus inf to 30 with an open parenthesis of 30. And so that meant that speeds that are less than 30 get into this group. If you're 30, if you're on the right-hand endpoint of this interval, you're not in that interval, you're in the next one. The one from 30 to 60 includes the 30, but the parenthesis at the end indicates that a 60 is not in that group, it would be in the next higher group. Right equals false is making this work. If you'd said right equals true, then the groups would be slightly different. Everything up to and including 30 would be your slow group. So that's a little bit easier to see when you don't have a labels argument. And when you do, you just get the labels. Okay. Third family, data verbs. So remember, these are the R functions that take a data table as input and give you another data table out. So we're going to learn a lot of these in this chapter: summarize, group by, mutate, filter, select, arrange, and there's a whole bunch more, but these are really the big ones. And once we've learned about a few of them, we can really start to do some wrangling. So what's the typical code pattern here? How do you actually instantiate the wrangling in using dplyr? Well, quite often you'll use group by and summarize together. And you'll see a pattern like this. You'll start with a data table, and you'll pipe it. And that means it's becoming the first argument to the call to the function group by. Subsequent arguments are the variables that you're going to do the grouping by. Those are going to be variables inside that data table. And the resulting group data table is going to get piped in as the first argument to summarize. And summarize is going to say, hey, I'm going to make a new variable that is gotten by applying some reduction function to a variable that is in the original data table. It needs to be a different variable than whatever variables I might have used to group by. So not variable 1, not variable 2, maybe some other variable, variable 3. That's the general pattern. So you can apply that reduction function to any variable that you did not group by. You can also apply certain reduction functions to no variable at all. We'll see examples of that. So let's get work toward an example. that function in that we talked about, that reduction function in, what does it do? It counts how many rows there are in a data table or part of that table. So for example, take NCHS and type that data table in as the first argument to summarize, where we're creating this new variable called total, and it's just a call to in parentheses. And so what that's going to do is going to look through the entire NCHS data frame and count how many rows it found. 31,126 rows, because there were 31,126 people. Now, that's not very exciting, but it gets a lot better if you work it together with group by. So say you wanted to know how many people were smokers, how many were not, and how many didn't answer the question about smoking or weren't asked it. Then how would you get that kind of tally? Take NCHS, pipe it into a call to group by. So it's the first argument is this data table. But the variable you're going to group by is the variable smoker, which has the values no and yes. And also there are some NAs. Some people didn't answer the question. And then you take that group data table and pipe it into summarize, where you say total is in. And that total is, you could choose any name you want. I'm just choosing total because it makes sense. You could just say George. It would just then be hard to understand. But the result is this very small data table with 3 rows now. The in function, the reduction function in, was applied to each group in the original data table. It was applied to the no group, and it counted up how many rows there were. Applied to the yes group and found 4,126 rows like that. And the NAs became a group, and there were 1,751 people who weren't asked about smoking. Group by and summarize. So just to kind of get an image for this, summarize doesn't want all the information. It just wants a little number for each group. And group by makes those groups. So like it's kind of working like you see here. If every row was like an M&M, the group by is sorting the M&Ms out into groups according to their color. Now, it's totally possible to group by 2 or more variables. Take NCHS, pipe it into group by as the first argument, but the second and third arguments are the variables smoker and sex in the NCHS data frame. So that means you're going to be looking at smokers who are male, smokers who are female, non-smokers who are male, non-smokers who are female, a lot of groups. So if you pipe the result into summarize and you create your total column, again with a call to in, then you get a little bit finer tally. So reduction functions will vary in this group by and summarize type of pattern. Think about the Math 111 survey data table in the TigerStats package. So just in case you haven't seen it before, although you highly likely have, let's go ahead and do a little bit of review. Head to RStudio, and let's read it in as data. And why don't we just view it? Capital VU in 111 survey. And so this is a data table with 71 rows, 1 row for every student that was surveyed in Math 111 some years ago. And you have such things as their height, their ideal height that they would like to be, how many hours of sleep they got last night, the fastest they ever drove a car in miles per hour, how they feel about their weight. Do they feel underweight, about right, or overweight? Do they believe in love at first sight? Yes or no, etc. And so here, we're taking M111 survey, and we're grouping by sex of the student and their seating preference. Do they want to sit in one front, two middle, or three back of the room? And we pipe that group into summarize, and we create a new column called mean GPA, and it's gotten by applying the function mean to the GPA variable in M111 survey, the grade point average of the students. Now, if some people did not answer about their GPA, then there would be an NA value. And that's actually the case for a couple of rows in the data table. So you can get the mean function to ignore those NA values and just take the mean of everything else by saying NA.RM is true as a second argument to the mean function. And sure enough, we get females, 3 groups of females, those who prefer the front, the middle, the back, their GPAs, and 3 groups of males, those who prefer the front, middle, back, and their GPAs. So do you see a pattern here to group by and summarize? The end result is going to be a little data table, probably much smaller than the original one. And the columns in it are going to be whatever variables you're grouped by, plus whatever new variable you created with the reduction function in the summarize step. All the other variables got kicked out. So just a remark, do watch out for NAs. If I had not said NA.RM is true when I call mean of GPA, then I would have gotten an NA for the mean of the females who prefer the middle because one of them did not answer the GPA question. Totally possible, if you like, to do more than one summary in your summarize function. So here I'm taking one M111 survey and grouping by seat, and then summarizing. I'd like a typical GPA, and I get that with the mean function. NA.RM is true. I'd also like to see what was the low GPA and the high GPA in each group, and I'm getting those with the reduction functions min and max, which also can use NA.RM is true. So go ahead and just be sure about that. And so now you can see we have in the resulting summary table a column for the one variable we grouped by, and then the 3 new summary variables we created in the summarize function. Here we're going to use the sum reduction function to find the total hours of sleep in 2 groups of people, the males and the females. So M111 survey, we'll group by sex. There's going to be 2 groups, male and female. We'll summarize. New column total sleep is the sum of the sleep values. So you're going to add up the sleep numbers for all the males. You're going to add up the sleep numbers for all the females. You're kicking out the NA values when you do that. And so the females slept a total of 253 hours, and the males slept a total of 201 hours. Now, the important thing in the syntax is that summarize requires these names. So the arguments to summarize will always be desired name, an equal sign, and then the call to your reduction function that creates that new variable. So total sleep equals reduction function sum applied to the sleep variable. So let's go back to our target graph. How would we get it? Well, thinking back to our wrangling plan, we're going to start with the NCHS, and step 1 was to drop the people under the age of 20. Well, you can do that with a data verb called filter. So filter will take a data table and it will return a new data table with only the rows that satisfy a Boolean condition that you stick in those parentheses as input. The Boolean condition here is age bigger than or equal to 20. So whenever the age of the person really is bigger than or equal to 20, we will keep that person. Next, wanted to turn the age in years into this new age group variable. We just wanted to add an age group variable to the data table. And so what we're going to do there is use a data verb called mutate. Now, mutate takes a data table and then throws on a new variable, a new column to it. And the way you use it is you say the name of the new variable that you would like. So it could be anything you like. I'm calling it age group. Then an equal sign, and then a call to the transformation function that you want to use. We're going to use the cut transformation function. And it's going to be applied to the old variable that is inside this data table, the age of the person. We're going to set the breaks to be 20, 30, 40, 50, 60, 70, 200. And there's nobody under 20 left after we filter, so we're going to get a group from 20 to 30. We're going to get a group from 30 to 40, 40 to 50, 50 to 60, 60 to 70, and then like nobody's 200 years old, so this is the same as 70 years old or more. I could have used an inf instead of the 200 to get the same results. And then the desired labels, 20s, 30s, 40s, 50s, 60s, 70 plus. Notice those do have to be in quotes. And there's going to be one less of these labels than there are breaks to make it work out. Right equals false. And so same effect as before. Include dot lowest just means including the lowest value in each of these groups. So after that, step 3 was dividing up the table into separate groups for each group, age group, and sex. That's going to be done with the group by data verb, and the two variables we're going to group by are the new variable age group and the old variable sex. And then we want to compute the mean height for each of these groups. So we'll use summarize on that. Our name, I'll call it mean height, and it's just going to equal this call to the mean function. We take the mean of the heights in each of the groups, saying na.rm is true just in case somebody's height did not get recorded. And so how does that look? Well, here's the wrangling procedure. And I'm just going to copy and paste this and go to RStudio and give it a try. So I'll give it out here in my notes. So what we got here, age group height shall be, see the assignment operator, shall be the result of starting with NCHS and then doing all this wrangling. So let's just do it first. And so now we get age group height here in our global environment, and I'll pop it up for a quick view. And it's exactly what I wanted. You know, we got the mean height for each of the possible groups, all the way from the people in their 20s to the people in their 70s. Now, when you study that code, because you're the one that designed the wrangling, you're going to know how that code works. But quite often, you'll be studying somebody else's wrangling code, and it's going to be this sequence of piped commands. And you might be wondering, like, how did they get what? How did they get this stuff? How is their code doing the work that it's doing? And when you have that question, it's always a good idea to work like this. Take a name and bind it to the result of, all the wrangling. And then run it a little bit at a time. For example, let's do age group height just down through the filter, okay, not including the pipe. And so we'll say that we want to run just that little bit. So if I hover over run, it says run the current line or selection. So it's going to run that selection. And so age group height is quite a big data table over here in the global environment. It's got over 15,000 rows because there are more than 15,000 people who were at least 20 years old. Otherwise, it looks the same as the original NCHS. It's got all the same variables. It's just that the ages are all over 20. Alrighty, let's try it down through the mutate, where you created the age group variable with the cut function. So let's run that. And age group height has changed very little. It has the same number of rows, but it does have one extra column. If we pop it up in the view, go way at the end, you see that new column has been created. Okay, let's try down through the group by, but don't include the pipe. Let's run that. Age group height has the same number of rows as before and the same number of columns as before. And when you pop it up in the view, it looks exactly the same as before. But it's not exactly the same data table. No, it's not. And we can tell that with a little comparison. I'm going to just get the old age group height after doing the age group variable. There we go. And now I'm going to ask in the console for the class of this object, age group height. And it says data.frame. Okay. And now I'm going to run down through the group by. And then I'll go in the console, up arrow, get ask for class of age group height again. And some stuff has been added onto the class. Not only is it of class data frame like it was before, it's of class other stuff, and most importantly, it's a group data frame. So although what you see in the view is the same as before, actually some information has been added on kind of to the side of the data table, an index, if you will, telling R where to find all the members of each of the different groups. And if you send a group data frame to a summarize function, which is going to happen next, that's how the magic of summarize is made to work. And so the last step, run it all, and we get down to just the 12 rows, one for each of the groups, and the 3 variables, 2 for what we grouped by, and then the new one we created with the summary as we saw. So if you ever see a bunch of long wrangling code that you want to understand, study it in its pieces by binding a name to the result of the long wrangle, and then just run line by line and investigate in the way that I've done. So now you can go for the graph. Now that you've got this glyph ready age group height, you can do ggplot, where your data is age group height, aesthetically mapping the x-axis to the age group, the y position to mean height. We wanted 2 line graphs, one for the guys, one for the gals, so we need to include the aesthetic color equals sex somewhere. I'll just go ahead and do it right up here. And we also need to say group is sex because, as we have learned, the ggplot is going to have some trouble drawing those lines correctly within each group unless you tell it what the groups are with this aesthetic called group. And then you throw on your points. You can control the size, and to get those squares, you actually say shape is 15. There's like 25 different shapes from 1 to 25. You can look them up on the web. And you want lines to run through the points, so a geom line. And these geom point and geom line, they're going to inherit these aesthetics from the first ggplot command. So in particular, they're going to know that color is equal to sex. And you throw on labels. And that's going to get you that target graph that we saw earlier. And so you'll win the admiration of people for being a master wrangler. So that's all for now. We'll take up wrangling in several subsequent screencasts as well.